In this lesson, we're going to be looking at pH and how it is related to the concentration of hydronium. So to get us started, we really need to look at what's going on in water that's just by itself. We don't have anything dissolved in it, it's just pure water. And so when water is sitting by itself, we usually think that there's just billions and billions and billions of H2O molecules, and that's all there is. And for the most part, that is predominantly what's present. But in water, we also have what's called autoionization. And what that means is some of the water molecules are going to react with other water molecules, and they're going to behave like an acid and base. One water molecule will donate a proton to the other water molecule, and when that happens, the first water molecule will gain that proton and become H3O positive. And the second water molecule, the one that gave away the proton, will produce hydroxide ions, which is OH. It lost a proton, OH minus. And so this is called autoionization. It happens to a very small extent. Most water molecules stay H2O, but some of the water molecules, like 1 in 10 million, react and form hydronium and hydroxide. And so again, this is called autoionization. Ionization. And it's because auto means self, and ionization means to become ions. And again, this happens to a very, very small extent. And when this happens, the concentration of hydronium in this water autoionization is equal to 1 times 10 to the negative 7 molar. In other words, in 1 liter, only 1 out of every 10 million molecules will actually undergo this autoionization. And because there's a 1-to-1 ratio of hydronium to hydroxide, the hydroxide concentration will be exactly the same. 1 times 10 to the negative 7 molar. And so because they're exactly the same, the acid part of the water, hydronium, and the base part of the water, hydroxide, are exactly the same concentrations, the water is still neutral. And so it still has a pH of 7. And what I want you to notice is when you guys know that water has a pH of 7, and look at this exponent in this concentration of hydronium. There's a 7 in there. And that's not a coincidence. The pH actually does relate to that 7, and we'll talk about that more in just a little bit. So let's think for a second. If I started putting some acid into this water, what is going to happen to the hydronium concentration, and what will happen to the hydroxide concentration? Well, think about that for a second. If we put acid in, we've said that acid produces hydronium in water. So as we add more and more acid, the hydronium concentration will increase and increase and increase and increase as more and more acid is added. Okay, so as more acid is added, the hydronium concentration will increase. As the hydronium concentration increases, the hydroxide ion concentration, the part that's a base, will decrease and decrease and decrease. And so as the acid increases, the hydronium increases, the hydroxide will decrease. And they are inversely related to one another. So we've talked about inverse relationships before, but an inverse relationship says that the product of your two variables, in this case the hydronium concentration and the hydroxide concentration, will equal some constant. And in this case, it turns out that the constant is 1 times 10 to the negative 14 for the product of the hydronium and hydroxide concentration. And this is actually a very useful relationship, because now if we know the hydronium concentration, H3O concentration, we can also calculate the hydroxide concentration, the OH concentration. But their product will always equal, for any solution, 1 times 10 to the negative 14. This is the first equation that you need to know out of 4 equations that we're going to be talking about with acids and bases. So let's look at some numbers of hydronium concentration and hydroxide concentration as the acid concentration increases and decreases. So for a neutral substance, we said that the concentration of hydronium is 1 times 10 to the negative 7 molar. If we start adding acid, and we're going to increase our acid going this direction, if we add more and more acid, this concentration of hydronium, and let me write down again what we're looking at, hydronium, H3O positive, is going to increase. So as we add more acid, eventually we'll get to a concentration of hydronium of 1 times 10 to the negative 6 molar. and then we'll get to a concentration of 1 times 10 to the negative 5 molar, and then we'll eventually get to a concentration of 1 times 10 to the negative 4 molar, etc., 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 until we eventually get to 1 times 10 to the 0 molar, which is just 1 molar. And so as we continue increasing acid, you'll notice that our exponents go from negative 7 to negative 6 to negative 5 to negative 4, all the way down to 0. And remember, what we've talked about in the past is that the pH of acids is less than 7. And look at this. 7, 6, 5, 4, all the way down to 0. So on the pH scale, this would be a pH of 0. This would be a pH of 4, pH of 5, pH of 6, and pH of 7, because the pH relates to the exponents of the hydronium ion concentration. Now notice all these exponents are negative and the pH scale is positive, and we'll talk about how that comes about mathematically in just a minute. Now let's say that we start decreasing the amount of acid, which means we increase the base of the substance. In other words, how much base is in the solution. So as we do that, the hydronium concentration will start decreasing because bases do not make hydronium, they make hydroxide. And so the hydronium concentration will start going down, 10 to the negative 8 molar, and then 1 times 10 to the negative 9 molar, and then 1 times 10 to the negative 10 molar, and it will continue decreasing into a normal, kind of a low range of 1 times 10 to the negative 14 molar. And if you recall on the pH scale, we said that anything less than 7, greater than 7, is a base. And so here we have a pH of 8, which corresponds to the exponent of the hydronium concentration. Then we have a pH of 9, pH of 10, and all the way up to 14. And now we start seeing the bases of our pH scale, these exponents for the concentration of hydronium. And that's what pH is based on, the concentration of our hydronium and the exponent that 10 is taken to for that concentration. So let's look at the equation for pH. The equation for pH, the way we can calculate pH, is pH equals the negative log of the concentration of hydronium. Now if you want to go back and review logs just briefly, I have another video and you're welcome to watch that, and I'll explain again what logarithms mean. But a logarithm simply is a way of calculating what exponent 10 has to be taken to get a certain number. And so if we take all these concentrations of hydronium and we put them into this equation, it ends up telling us what 10 is taken to in order to get the hydronium concentration. Let's look at an example of this. Let's say that I have a concentration of hydronium that is 8.7 times 10 to the negative 3 molar. And we want to know what the pH is. Well, pH is all about the exponent 10 is taken to in order to get this number right here, 8.7 times 10 to the negative 3. What exponent does 10 have to be taken to get this number? And it's going to be near 3, okay, or negative 3. So we're going to find out what that is. So to calculate the pH, we take the negative log on your calculator of 8.7 times 10 to the negative 3 molar. And the negative here is going to cancel out the negative exponent. And that's why I was talking about positives earlier, is that the negative in our equation will cancel out the negative of the exponent. And so on your calculator, you'll type in a negative, not the minus sign, but the negative sign, negative log, and then you'll put in this number. Make sure you use the EE button. Don't use times 10 and caret. So when you plug that in, you get a value of 2.06 for your pH. And pH does not have a unit because, again, pH has to do with exponents, and exponents can't have units. So our answer is 2.06, and notice that this is in the acid range, and we have a fairly large concentration of hydronium. And so this is an acid. Our hydronium concentration represents an acid, if you remember from our previous chart, and we have found our answer. And again, what this represents is the exponent that 10 has to be taken to in order to get 8.7 times 10 to the negative 3. And if you do this on your calculator, you'll actually get the answer. And remember, we had a negative here, so I'm going to make this negative. So 10 to the negative 2.06 will give you 8.7 times 10 to the negative 3, the concentration that we solved for. So the pH is 2.06. So this is our first pH calculation. Let's try another one. Let's say that you have a base this time, and the H3O concentration in the base, remember, bases don't make H3O positive, so it's going to be very, very small. The concentration of hydronium is 2.79 times 10 to the negative 8 molar. And we want to know again, what is the pH? So, to solve this problem, we write our equation, pH equals negative log of the hydronium concentration. Remember, the pH is going to be very near the exponent here. So our pH should be in the ballpark of 8. Let's go ahead and plug in our number and solve for this. So the pH of negative log of 2.79 times 10 to the negative 8. And when you solve this on your calculator, plug in a negative, push the log button, and 2.79 times 10 to the negative 8, and you should get your answer. When you do the calculation, you will get 7.554, and that will be our pH. Notice that that is in the base range, but it's just slightly basic. We're just barely above 7 here, and so this is not a strong concentrated base. This is a very weak dilute base that we have here. Another thing to notice is significant figures. Logarithms are a little weird. When there's 3 significant digits in the number you're using, that's not how many total significant digits you get in your answer. That's how many total decimal places you'll have in your answer. And if you would like to know more of why that's true, please feel free to talk to me in class. I'll explain to you why that's the case. But with significant figures, if however many significant figures are in the number you're taking the logarithm of, that's how many decimal places you have on your final answer of pH. So this is our second example of pH. But what about if you have to go backwards? What if you're given the pH and you need to solve for the hydronium concentration? What do you do then? Well, let's look at the equation and see the equation, how it can be rearranged to solve for that particular problem. So here is our original pH equation. If we start rearranging to get the hydronium concentration by itself, I need to get the negative to the other side. So I get negative pH equals the log of the hydronium concentration. And now we need to do the opposite of log. And the opposite of log, if you actually look on your calculator, is what's called anti-log. And it's simply 10 to the exponent. And so what I'm going to do is I'm going to take 10 to the exponent of both sides. 10 to the exponent of negative pH and 10 to the exponent of log hydronium. 10 to the exponent is the opposite of log, and so that ends up canceling 10 to the log. And so we end up with an equation 10 to the negative pH is equal to the hydronium concentration. And this is just a rearrangement of our original equation. If you're familiar with logarithms, then you can just rearrange this yourself each time. If logarithms give you a tough time, then this might be a good equation for you to learn, that when you're solving for the hydronium concentration, you simply take 10 to the negative pH of that's given to you. So let's go ahead and solve a problem here and see what it looks like. Okay, so let's say that you have a solution that has a pH of 4.92, and we want to know the hydronium concentration, H3O positive. How are we going to solve this? So again, we're going to look at our equation, which is pH equals the negative log of the hydronium concentration. We plug in for pH. pH equals 4.92. It's the negative logarithm of the hydronium concentration. And when we rearrange this equation like we did in the previous example, when we put the negative on the other side and take the inverse log, we get the hydronium concentration is equal to 10 to the negative pH. And so when you solve this on your calculator, you get your hydronium concentration to be 1.20 times 10 to the negative 5, 10 to the negative 5 molar. And that's our hydronium concentration. And inverse logs can be a little tricky, but as long as you're careful with your math, you can solve for those hydronium concentrations without too much difficulty. So just a couple of notes real quick, a couple of reminders. When we're talking about hydronium, H3O positive, that also can be written as H positive. Either way is a fine way to write the concentration of hydronium. Another thing to remember is that when we have a strong acids such as HCl dissociate 100%. In other words, every single molecule of HCl will split apart into hydrogen ions and chloride ions. And so if I give you the concentration of HCl, like let's say that I say the concentration of HCl is equal to 0.02 molar, what I'm telling you, because this is a strong acid, is that the concentration of hydrogen ions is equal to 0.02 molar. The concentration of the acid is the hydrogen ion concentration. Or another way we could write it, the hydronium concentration is equal to 0.02 molar. And so when you know the concentration of the strong acid, you know the concentration of hydronium. Keep that in mind as you solve problems for pH. So in the next lesson, we'll talk about pOH and how the pOH is related to pH.